Hello, my name is Michelle, and welcome to my channel where we solve the LeetCode problems together. If you are preparing for technical interviews or simply want to improve your problem-solving skills, then you're come to the right place. In today's video, we will be tackling problems number 509 Fibonacci number, and I will be walking you through the thought process and technicals needed to arrive at the optimal solution. We'll be coding solution in Python, so make sure to have your editor, the IDE, or the LeetCode platform ready. So grab a cup of coffee and get comfortable. Then let's dive into today's problem. So before we starting to do any actually coding things, let's first go through the problem description first. I know probably most of you already know what is Fibonacci number, what are the concepts there, but in case there are some of us still the very first time to know this term, to get familiar with what each Fibonacci number is, then we will go through the description again first. So the Fibonacci numbers, commonly denoted f of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. That is what we can say from these two equations here. So again, the sequence starting from 0 and 1, and then each subsequent number is the sum of the two numbers that came from before it. So the sequence will be we're coming from f of 0 is equals to 0, f of 1 is equals to 1. So for the second number, f of 2, which will be equals to the sum of the two numbers that came before it, which is f of 0 plus f of 1, which will be equals to 0 plus 1, which will be 1. So if we calculate all the numbers, we will get a sequence something like 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. So if you search a lot of things online, you can see these numbers appear frequently in nature, mathematics, and computer science, and have many interesting properties and applications. But today we are just focusing on how to solve this problem, then we're coming back to here. So for this problem in particular, we just have the question very straightforward. We have this concept, will be given a number of n, then what we need to do is just we calculate what would be the Fibonacci number of n. So let's go through this example to get a better understanding of this problem. So assuming our input is n equals to 2, so then the output will be 1 because Fibonacci number of 2 will equals to f of 1 plus f of 0, which is a base case 1 plus 0, which will be ended with 1, so the output will be 1. Then we come into example 2, the input n is equal to 3. Actually, that is the continuous number after 2, right? So after coming up to 3, then we will have the Fibonacci equation with f of 3 equals to f of 2 plus f of 1, which is f of 2 is 1, we just calculated in previous example, and the f of 1 we could find it in the definition, which is 1, so that would be 1 plus 1, which is equal to 2, so the output will be 2. So similar situation for example 3, we will have the Fibonacci number of 4, and that will be equal to the Fibonacci number of 3 plus Fibonacci number of 2, which will be 2 plus 1, will be ended with 3, so we have the output as 3. So currently this problem is quite simple and easy for the description here, and the whole approach, always say the thing we want to do is very straightforward. So nothing we need to focus on how we understand the problem here. Then for next step, we're going to solve this problem. So we're going to do 5 different approach to solve this problem today. You may wondering for this kind of easy things, why do we need to using all these different kind of ways? Because from this example, I would take it as an example to show you guys when we go through an interview process, normally what kind of things we need to take into consideration, and secondly we want to say how do we optimize our solutions, and what would be the considerations, especially for the dynamic programming problems. Okay, so we're starting from the very scratch, the very like brute force one. Like, how do we just translate the definition into the Python coding? Then that would be a very like straightforward translate. You don't need to consider about like time complexity or space complexity. You just need to translate whatever you can see from the equations to the Python. Then you will get your very first like solution. So we can call it as maybe just a recursion approach. So for this recursion approach, we first of all we need to do is to set up the base case, right? Because for the very beginning, we have the base case as like the Fibonacci number of 0 is equal to 0, Fibonacci number 1 is equal to 1. So we will have is if the n is less or equal to 1, then the Fibonacci number will be just itself. So we just return n. And if that n is larger than 1, then we will continue to the second equation, which is f of n equals to f of n minus 1 plus f of n minus 2. So here we can see like it kind of a repeated steps for each level, for each phase. So what we need to do, or what we want to do here, is we're just using the function itself as a recursive function and always reach out to the bottom, then sum the each level of the values back up to the top level, then we return the value. So from the coding perspective, what you need to do is just to return self.Fibonacci number, the function. Here we call it as fib. Then self.fib, we have the first item is n minus 1 plus self.fib. The second item is n minus 2. So from here, we can say like for each level, we'll go to one level deeper to say what would be the number for Fibonacci n minus 1 plus n minus 2. And if we reach out to the all the way to the very lower like level, like n equals 2 or less than 1, then we will have some numbers there. Then we will add all those numbers and back up to the very top levels, and at the very top level we'll have the final answer. So this will be our very first approach. Let's submit the code and evaluate it. Okay, so the test already passed and it is got accepted. So this is our very first approach, but does this approach is good enough? Like from here, we need to consider from two perspectives. Normally, we will have these two. We always have other like considerations, but we will first starting with these two. The first one is called the time complexity, and the second one is called the space complexity. So for the time complexity is like how many operations you need to do. We have different ways to calculate or we say to represent the time complexity. In most or majority of the company, when you do the interviewers, you will have them to evaluate the time complexity and space complexity from the big O. So from big O, we want to talking about like the highest number or the level of the complexity. So you might have like each component have different levels of complexity, like n to 2, or we say n or n log n or just log n. But we will always keep only the largest like level. So from this example particular or this problem particular, since we're going to have levels of the recursive, and for each level we'll have two elements, right? And for each element, so kind of like we'll split into like two lower down for the recursive steps, and for each level of the recursion we group like exponentially as the depth approaches of n, because we're starting from n and all the way to the bottom, so the depth would be approximately like n depths. So here we have the time complexity as O of n to O of 2 to n, and for the time space complexity, even though we didn't actually create anything here, but within the middle of the recursive steps, we actually will using some of the physical memory space to store the intermediate like numbers, like what we have the numbers in between. So we will have the space complexity as O of n. So this is our very first approach. Then we have to notice here, if you say something or whatever the problem is or whatever approaches you have, if you say the time complexity is O of 2 to n, which is exponentially, normally it will not meet the interview like the threshold, or you cannot pass the interview just within this time complexity, because we would love to have the time constantly get rid of exponentially. Otherwise, it always have a very high risk, like it will run in an extremely long time and you cannot meet the standard like expectations. So if you say anything like the exponentially level of time complexity, you will always need to think how I will optimize my solution. Then that will coming up to our second approach. So for our second approach, nothing special we need to changing within our current like implementation, but instead of we're going to like just using this script, we're going to introduce a new like built-in function, which is called add cache. So for the add cache, this function, what we do here is like when we calculate anything from the Fibonacci number, if that one is already calculated, we want to store and memorize in some place. So next time when we say it, we just need to go into the cache and grab the number. We don't need to recalculate again. So what does it mean, or what is the benefit there? We take an example as n equals to maybe 5, right? And for the next level, when we recursive it, we will have 5 f of 5 equals to f of 4 plus f of 3, right? This is our definition for Fibonacci. And for next level, for 4, we will have 3 plus 2. So here maybe I will add this part because that will make more sense here. So f of 5 will equals to f of 4 plus f of 3, right? So we will have this equation here. And for f of 4, we will have f of 3 plus f of 2 here. Then similar things for the f of 3, we will have that as f of 2 plus f of 1. And we were doing the recursive steps even further. So f of 3 will again equals to f of 2 plus f of 1. And f of 2 will equals to, we will say f of 1 plus f of 1, right? And we will repeat all the things again and again until we reach out to the end. Like for this level, we have f1 and f1, and for f1 it's already in the base case, so we just return the result, the actual number. So that will be 1 plus 1. Then we will back up to f of 2. Then we will have 2, right? So this is what we did. And you can see here, even for f of 5, we repeatedly or we do calculate the f of 3 for twice, f of 2 for like 3 times, and we always need to go through the f of 1, but this is the base case, so we don't need to take that into consideration. But you can see like we need to do some redundancy, always say repetitive like steps to calculate the same number. So for the add cache here, what we need to do is for the very first time when we calculate f of 3, we will memory that into our cache. So next time when we say f of 3 here, we don't need to calculate the following like recursive steps again. What we need to do is we just come into the cache and get the number to say, oh, I already calculated f of 3. Then what is the number? We get the number, then just directly add them. So we don't need to go through the recursive steps here again. So in that case, we can dramatically like reduce what we do for the like time complexity. So let's submit this one first and say if that makes sense. Okay, I have something wrong here. Oh, okay. Yeah, I probably did something wrong here. So I need to do the add cache before the define function. Let's submit again. Okay, it's already submitted and already accepted. So from here, we can say like previously we have the time complexity as the level of the exponential level, which is 2 to n. And now we have the time complexity reduced to O of n, which is dramatically reduced, right? It kind of lower, like not only one level, kind of if we say different like levels of the time complexity, at least 2 or 3 levels here. And we can see the space complexity here again. Unfortunately, from this approach, we didn't actually improve the space complexity because even though we're using the add cache, the building function, we still need to go through the recursive steps. We still need to remember some of the values in the middle. So we have the physical in the level of the physical memory in the level of n. So we have the space complexity as the level of O of n. Okay, this is our second approach, and we can go to our third approach. So for the third approach, we can see here, like now I'm as an interviewee. I told you like you cannot using these building functions. Then what would you do? So if we cannot using this building function, what we need to do is we are going to think like how can we using Python like scripts to write this approach. From here again, we need to reflect what we have here. So for the cache, what we need to do here is we memorize everything we already calculate. So what about like we just create a space and memorize whatever we already like calculate and just put that into that space, right? So kind of what we need to do here is we just manually create this space for us to store the how would say the store the middle like the intermediate like value here. So the cache would be 0, initially everything with 0 and space with n plus 1, and we also have the cache 1 is equals to 1. So the why do these steps? Because for the base case we have f of 0 equals to 0, f of 1 equals to 1, right? Then for next steps, what we need to do is we calculate. When we calculate, we need to, for each steps, we store the values to here. Then in this case, we can just calculate from bottom to up, right? We don't need to always coming from like the top down approach, like from the very large number to the very smaller number. We can actually from the smaller number to all the way to the numbers we want. So in this case, what we need to do is we can actually using an iterative like approach to solve this problem. So for I in range of 2 to n plus 1. So first, why 2 here? Because we already have the base case covered for 0 and 1. So the next one we need to calculate is from 2. So why n plus 1? Because when we say range, n plus 1 doesn't include it into this iterative step. So if we say n plus 1, it will for loop keep the iterative steps all the way till I equals to n, right? And we need to find the number of n, so n is our upper bound. Then if we want to include n, we have to do is n plus 1 here. Okay, so for each iteration, what you need to do is we just calculate the new numbers for the cache. Then the cache of I would be equals to cache of I minus 1 plus cache of I minus 2. So this is actually exactly the same thing, the same equation, what we see here, right? Exactly what we want to approach for the concept here. And after all the way we calculate all the like for loop steps, the last step is we have all the things at the end for the cache. Then for the cache of n is what we want for the n is what we actually calculate for the n Fibonacci number of n. So let's submit the how to say let's submit the solution again, and we can say the solution already accepted. So that is our like the I guess the third approach here. Okay, so from this approach, let's say about the time complexity oops, I'm sorry. Let's say about the time complexity and the space complexity. So for the time complexity, we now previous steps we using the cache function. We have the time complexity as O of n. Now we still have the time complexity as O of n, right? Why? Because we need to go through for loop, and for the for loop we have n iterative steps. And for the space complexity, since we need to create this cache space, so we have that space up to the n level of the space complexity. So we have the O of n here. And now we think how I can even push the optimization of my current approach. Do I want to keep push the time complexity to optimize time complexity? Probably won't, right? Why not? Because we always need to go through all the way to the end, so we cannot improve the O of n in any ways. We might somehow to approach a better solution by increasing the execution time, but we cannot actually improve the level of the time complexity, especially in the O level, right? So the time complexity, I will stop here. Then I'm thinking about the space complexity. So for the same space complexity, we can say what we do here. For the cache, for each iterative, we calculate and stores and memorize the values we got. But for the value or the numbers we get here, we only use the next following two iterative steps, right? Because that one only matters for the two preceding ones. After two following iterative steps, we don't need that number anymore. So in this case, do we want to always keep all the numbers here? Probably we won't. What would you do? It would just keep what we calculate here, and we keep the numbers for the two preceding ones, right? So what we need to do here is we are going to not create the cache space here, but instead of there, we create three variables. The first one is current, which means the current ones we're going to calculate, and we have the previous one. You can see the number as previous means preceding ones, and one means the steps from the current number to the previous ones. If we say one, then we say that is the previous one, the position of the current one. Then we will initialize with 1, and the previous 2 is we have 2 steps from the current one to the previous one. So because when we calculate with from 2, so for the 1 steps we have f of 1, which is 1, and from 2 steps we see that from the preceding perspective, so that would be f of 0, which would be 0. So we initialize f of 1 to 1, we initialize f of 2 to 0. Then we're still doing this for loop, but instead of we memory everything into a cache space, we kindly just to do is current equals to previous 1 plus previous 2, because we just get the numbers for the current stage. And since for next iteration, the previous one will coming up to the previous 2 for the next iteration, and our current calculation result will be the previous 1. So we need to update these 2 variables correspondingly, and then we go to the next iterative steps. So we keep all the for loops again until we reach out to the end. After the end, we calculate everything out. Then for the very last one, we calculate the current value would be our final output. So for the very last iteration, we calculate for I is equals to the n, then what would be the Fibonacci number for number n, right? Okay, before we talking about the time complexity and the space complexity, let's submit it first. So everything is accepted, so that is a good sign. And we're coming back to the level of time complexity and space complexity. So as we said just now, the time complexity is always keeping off n here, because we need to go through the n numbers. And for the space complexity from this approach, the fourth one, we kindly reduce that from O of n to O of 1. Because previous one, we have calculate, or we say we always have a space of the cache equals to the length of n to store of the, or we say memory of the numbers there. But from here, we just need 3 variables to keep updates and keep the memory of the numbers we need to use. So 3 means a constant number. Constant number equals to the space complexity is on the constant level, which is O of 1. So from here, we have the time complexity as O of n and the space complexity as O of 1. So this is the best approach, or the optimized approach. But at the very last step for our today's video, I still want to show you another way, because from the third one approach, we're starting to thinking like we're using the bottom up like approach. We always calculate that from the we calculate that from the smallest number to the up to the n number, so like from the small number to the large number. But what if I really want to calculate everything from the large number to the smaller number? What do we need to do? So from here, what we can do is we're still using the recursive function, but how do we get rid of the exponential one? We're still using the memorization approach, right? So from here, if the n is in the self.cache, so from here we still create a cache function, cache space, but instead of like we create that within the function, we create outside of this function. So we will say the 0 is matched to 0, 1 is matched to 1. So this is basically the same thing as what we do for the base case. And from here, if n is in the self cache, then we return the self of cache n. Otherwise, we will just go through the recursive steps as self.cache of n. And oh, I'm sorry, that should be the smaller letter of n, my bad. So if the self of n, that would be the self of Fibonacci n, I'm sorry, n minus 1 plus self dot Fibonacci n minus 2. Then we will calculate the result and just add this number back into the cache. So next time when we to say the same number, we're going to the if statement first. If we already calculate that number already, then we will just directly get this number instead of we recalculate. So currently we're using the same concept in the second approach, but we just, instead of using the bottom up approach, we're using the top down approach, which means we calculate from the largest number to the smallest number instead of from the smallest number to the largest number. Then at the end, we just return the self.cache of n. Okay, I'm sorry, that is the small n. I don't know why I keep using the capital N here. Okay, let's submit this solution. So we still successfully passes all the test cases and accepted by the system. So from here, we get our final approach. Then let's now consider the time complexity and space complexity here. For the last approach, we have reached out to the very top optimized solution as of n for the time complexity and of 1 for the space complexity. But for this one, since we're going back to the cache usage, then the time complexity will still be of n, because we don't need to recalculate everything if we calculate already. So the time complexity will still be of n, but for the space complexity, we go back to the of n here, because we're using the cache space here, right? We need to just memory all the things we calculated in the middle of somewhere. Okay, so this is all for today's approach. We have 5 different ways. Some of them are top down, some of the ways are bottom up, some ways are recursive steps, and some of the steps are actually just iterative approach. So what we want to do at the very end, or you want to show your interviewees in the interview, that would probably would be the approach 4, but that is very important for you to understand how it from the brute force, the very scratched approach, all the way to the best approach. So if you get understanding of this approach here, that will be a good fundamental for you to keep study and go further for the dynamic programming studies. Okay, thank you. That should be all for today, and I wish my video could help you in any ways for your study. And if you like my videos, please give me a thumb up. And if you haven't subscribed my channel, please subscribe my channel, and I could see you all in the next video. Thank you. Talk to you next time.